Started. For those of you that don't know me, my name is Joe. I'm going to be guest lecturing for this lecture on deep learning. So there's a big turnout here. So let's get into kind of the introduction to why we might want to learn about this. This is kind of the standard setup you might have in machine learning, at least for supervised learning, where you have some matrix of data consisting of examples with a certain number of features, and you want to associate those with some set of labels. For instance, if y is continuous, you might want to regress to a line that describes the relationship between your data and your labels. If y is binary or categorical here, you might want to try to classify what these labels are given your inputs. This is all within supervised learning, remember. So you can consider this simple example of trying to classify between these two sets of points here. We have some points that are labeled with the label y equals 0, and other points that are labeled with y equals 1. We have two data dimensions here, and then a bunch of points, each of which are an individual data example. So we have these dimensions x1 and x2, and we see that in this case, we're very fortunate because a simple line can separate these points. And so typically in this case, you're going to use something like logistic regression, where we're actually regressing to the logistic transform. But it's still a linear decision boundary here. So we've drawn a line in this space. And what we have is this logistic transform there on the left, and we're going to fit a line to that. This line is represented by this vector w, which stands for weights, and then maybe a bias term b, which just sets an offset. And we can rewrite this to give us a probability of the label being 1, given our data example. And typically in this case, we're going to try to minimize the binary cross entropy. So it just gives us a loss function in order to find the right set of weights and bias to actually fit and separate these points. And we're going to do this typically using gradient descent. In some cases, you can just solve for the best solution exactly. But this is kind of the overall pipeline of what you might get in a simple setting of just trying to classify these two different sets of points. But what if we actually had a different set of points? What if our points could no longer be separated by a line? What will we do there? Well, we need a nonlinear decision boundary. So we can't just use a line anymore. One thing we could try doing is just expanding out our data dimensions, right? So here I've drawn this kind of paraboloid looking curve, and what we could try doing is, well, say let's actually fit a parabola to our data and try to separate the points in that way. So that just involves kind of taking these higher order terms and using those along with, again, a set of weights. But another option would be actually to say, let's have multiple lines. Let's draw multiple lines to carve up the space in a certain way such that when we actually combine these lines, we get a nonlinear decision boundary. And so that's, in both of these cases, we see that we're transforming the data in some way in order to actually help us classify between these two sets of points. So it's all about kind of manipulating and shaping the data in the right way. Let's look at some simple Boolean operations. For those of you familiar with the AND gate, it's 1 if and only if the two inputs are both 1, and so we can see we can separate this with a line fairly easily. For the OR gate, it's 1 if either of the points are, or either of the inputs are 1, so we can again separate this with a line. But for the exclusive OR, the XOR, we can no longer do that. We can't actually just draw a line and separate these two sets of points perfectly, but we can see that actually by combining ANDs and ORs, we could draw multiple decision boundaries that would allow us to get the XOR. So it's not linearly separable, but we could separate this with AND and OR. So how might we build this network up? Well, you could feed in both of our data dimensions into an AND gate and an OR gate. And then we could take the not of the AND gate, just reverse that relationship, and then combine these two streams with another AND gate, and that would now give us a function that could actually perform the functionality of an XOR gate. So you've seen that we combined these linear decision boundaries here, and what we get out is a nonlinear decision boundary. So this is maybe a more systematic way of thinking about how we might build up these nonlinear decision boundaries. So just to recapitulate, if we want to deal with more complex data that doesn't have these simple linear relationships, we're going to need nonlinear functions. And we can form these nonlinear functions by composing stages of processing. And the number of stages that we have, we're going to call that depth. All right? You can think about deep learning as functions which have multiple stages of processing. Everybody on board with this? Yes. OK. So you might be asking, why didn't we just use the nonlinear terms? What was so wrong about that? That seems like a simple way to go about doing it. Well, you can. There's nothing saying you can't. But with enough linear decision boundaries, we'll see that we can actually approximate any nonlinear decision boundary. And so maybe we can go about this simpler method of just using linear decision boundaries and instead of having to consider all possible high-order terms. And that brings us to deep neural networks. So you may have heard about them. Maybe they sound intimidating, but they're really quite simple, as we'll get into. So the basic kind of building block of a deep neural network is the artificial neuron. Not to be confused with the neurons that are in your brain. They're actually quite different. But they're loosely inspired by biology, where you have some set of input features here, x1 through xm, and then I've also tacked on this additional bias feature, which we'll just set to 1. We have a set of weights denoted by these arrows here. Those lead into a summation, a weighted summation of your inputs. And then we're going to apply a nonlinear function to this summation, which will give us an output feature. We can take multiple artificial neurons here and combine them together to form a layer. So this is kind of the next level of abstraction, is the neural network layer, which, again, is just combining a few artificial neurons together. And then once we have a layer of these neurons, we can then stack these layers together to form a network. So we've gone from neuron to layer to network, building up a deep neural network. So let's actually get into what are the kind of the mechanics under the hood here. So each of these artificial neurons is really just computing this weighted sum and a nonlinearity. This sum here I'm going to represent with the letter S, and that just involves this dot product of each of the weights against each of their corresponding inputs here. So we can represent that again as this W transpose X. And then the nonlinearity here we're going to represent as this function sigma, which takes in S and returns some output H. So again, just to look over that, we have a set of weights, a set of input features, this bias term W0, which is just multiplied against 1, and this summation that results from that. And we're going to pass that summation through a nonlinearity to get an output feature. So I prefer to think about things in terms of visually what's going on. And so I like to picture it as having, that you have this one vector that's just multiplied against this other vector. That gives you this single scalar number here. Again, these are our weights, our input features, and our sum. And then we're going to apply the nonlinearity on that single scalar, which is going to give us a transformed scalar. So just simply applying a function to the result of a weighted summation. Now, what's going on at the level of a layer? Well, we can combine multiple of these weighted summations by actually taking all of our weight vectors, where each vector is corresponding to a neuron, and combine them into a weight matrix. So here we've taken all of our W's here and combined them into this capital W, which is representing this weight matrix. And we, again, just multiply that entire matrix against our input features to give us a vector of sums. And we apply now the nonlinearity element-wise on each element in the vector of sums, and we get out the resulting vector of nonlinear transformations. Again, graphically, just to think about this, you have, oh, it kind of got cut off, but you have a set of weight vectors that are each multiplied against your input feature vector. That gives you a vector of sums, and then you're going to apply the nonlinearity to each item in the vector, giving you a vector of output features. So graphically, I hope, does this make sense? Everyone still following? Good. So now when we get to the level of an actual network, let's first define the inputs here to be x superscript 0 here. And then we were talking about this output feature h. Well, let's actually call that x superscript 1. And you can think of so on and so forth through the network. You have x to larger and larger superscripts for each layer. Now, the first layer, we just have this weight matrix at the first layer multiplied against that input, giving us this sum vector. Apply the nonlinearity. That gives us now the inputs to the next layer, which are then multiplied against this weight matrix, and then apply the nonlinearity, or whatever nonlinearity is at the second layer, to give us now the features that go into the third layer. And you can imagine chaining together multiple stages of these operations to get very, very deep networks. So again, this is graphically a vector of inputs, x here, that's multiplied against a set of weights. You apply the nonlinearity, multiply another set of weights, nonlinearity, as you go through this function. So just to recap briefly, we have built up this machinery for building expressive nonlinear functions, as we'll hopefully see a little bit later. And these functions can actually be shown to be universal function approximators. So if you have enough units and enough layers, you can approximate any function that you'd hope to approximate. Now, I, again, like to think visually about this. So the way I tend to think about this is actually the dot product is actually the distance between a plane and a point. It's the shortest distance. So if you think about an artificial neuron defining a hyperplane in this space of however many dimensions you have, then actually calculating this dot product is the same thing as calculating the distance from a hyperplane. So calculating this weighted sum, we're just finding the shortest distance between whatever input point we have and that hyperplane. And what is the nonlinearity doing? Well, you can think about this distance function that emanates out from this hyperplane defined by the weight vector. And we're going to just transform that in some way, in a nonlinear way. So we're going to convert that distance that we just calculated into a transformed distance. So that's what's going on through this artificial neuron. And then if we think about, well, if one set of points shares a lot of features with a lot of other sets of points, there's some commonality there. Well, a weight vector could actually filter out all of those points by defining this distance from that cluster of points. So we can now start thinking about abstract features that we're clustering using these weight vectors. So if we think about the first layer, we're carving up the space of points that we have with a set of hyperplanes, one for each neuron. And then that's giving us these transformed distances that become the points in the next space. Now we carve up this space with a set of hyperplanes. And we continue this process until, for instance, for classification, we can now separate two classes of points with a single hyperplane. This is the kind of procedure that we're hoping to get out of having a deep network. That we can carve up these spaces of points with all of these linear functions until we get to a point where we can actually just separate these points with a single linear function. So this is the overall procedure we're looking at, where we're eventually ending up with separating out this cluster. So hopefully graphically this isn't too intimidating. It's a little bit unintuitive at first, but I tend to prefer this over just thinking about matrices and vectors only. So big picture, what are we trying to get at here? Neural networks are just functions, or really just function approximators. They're trying to approximate some function that you're trying to learn. They have this nested or deep structure that enables a broader set of functions, where really it's just the output is this neural network function applied to your inputs. And that's just a this nested structure of layers here. And in particular in machine learning, we often care about approximating conditional probability distributions. A lot of the more theoretical machinery in machine learning is revolved around the statistics of actually estimating probabilities. And so deep networks have become this indispensable tool for estimating these probabilities for really complex probability distributions. So big picture, that's what we're getting at here. Question?
Yeah, how do you choose W, especially when you add numbers of abstraction, like layers of abstraction?
Mm-hmm.
One classifying be really difficult. Not really have a training set at like layer n or n minus 1.
Yeah, so are you asking about how do you actually train, or how do you? Yeah, so we're just about to get into that. It's an excellent question. You have this gigantic network. How do you know what the weights should actually be? So we're going to get into the training algorithm in just a second. Any other questions while we're here? Good? OK, so exactly. Backpropagation is the way that we actually figure out what should these weights be? What should their value be? So we talked about neural networks as function approximators, but we actually didn't talk about how to actually find what function you're trying to approximate. So we have this gigantic network that, based on how we set the weights, could give us any number of different functions. So we have this hypothesis space of functions, but we want to really find the optimal function or something like that that approximates the function we are trying to approximate. So we're going to adjust the weights in order to do so. And the main technique for doing this is this optimization of gradient descent. So if we think about the loss that's defined by whatever metric we're using to quantify the performance of our model, we have this loss along the y-axis here, and then we have, think of this as just a single parameter that we might have in the network. And if we vary the parameter, we might see different values of that loss. So different qualities of fit, you might think, to the probability we're trying to estimate. And so what we would like to do is actually push the value of that weight toward where that loss is minimized. So this is just standard optimization through gradient-based technique of moving down this hill. So in order to actually learn the weights, we need the derivative of the loss with respect to the weights in order to say how should we update the weight in order to decrease the loss. And that's shown in this derivative here, partial derivative of the loss with respect to this particular weight parameter here. And in multiple dimensions, we can think of this as actually a gradient, not just a single derivative. So again, we talked about how this neural network defines this composed function of operations. And the loss here is going to be kind of the output of the network, or a function of the output of the network. And in order to go back through this nested function, we're going to use the chain rule, which hopefully you remember from basic calculus. And so we're going to go through this very brief example just so that everyone's on the same page about what we're trying to get at with the chain rule here. We have, for instance, this simple function y is w2 times e to the w1 times x, where we have this input x here, we have the output y here, and we have these parameters w1 and w2. And what we want to calculate are these derivatives here. So the derivative of the output with respect to each of the weights. And so we can just use simple substitution, plugging in or redefining v as this function here and u as this function here. And then we can go through and actually derive what is the derivative of the output with respect to the weight w2. Well, that's just this v here, because we have w2 times v. So that's just the term v. We calculate that there. But now actually to get to the weight w1, we see that that's nested inside of this function e to the w1 times x. So we have to use this chain rule to go back from dy dv to dv du, and then finally from du to dw1. And so by multiplying these terms together, we can get to the derivative of these internal sets of our, or layers of our function here. So this is the basic method by which we'll actually calculate these gradients. And this procedure, again, is called chain rule. So here's our network again. And we'd like to calculate the gradients with respect to each of the weight matrices. So let's start with this final layer of weights. So let's first draw the dependency graph. If we think about all the computations that are going on in this network to calculate the output, let's draw out what this actually looks like, where we have some operations that have taken place up to this point, represented with this ellipses here, and then we get to finally the x at the L-1 layer, and that's multiplied against these WLs, which gives us this sum here. We have this output, and we compare that with a target in some way, this label, and that gives us the loss. So if we think about defining this computational graph, well, we can draw the dependencies with these derivative arrows that are going back from the loss to our weights here. And this helps to show exactly where we need to calculate the derivatives using chain rule to get back to whatever set of weights we're trying to get to. So here's, again, that computational graph. And the overall derivative here, dl dw capital L, is this the derivative of the loss with respect to our output of our final layer. So this depends on the loss. We have now the derivative of that output with respect to the sum that it came from. So this, again, was calculated using that nonlinearity. So we can now take the derivative of the nonlinearity. And finally, the derivative of the sum with respect to the weights, which, because it's a linear function, just gives us the x at the L-1 layer. So now we've strung out this computation, used chain rule, and gotten the gradient with respect to the weights at the final layer. So how do we go further back in the graph? We'll draw the dependency graph again. And we have now more terms that are chained together here. So I won't go through in too much detail, but it's a similar idea of you have to follow this entire chain of dependencies all the way back to the set of weights that you're trying to calculate the gradient for. And you can calculate this all from chain rule. So if you're an astute observer, you'll see that actually some of the terms that appear, some of the same terms appear in both gradients. So specifically, we have this term dl dsl to the derivative of the loss with respect to each of the sums that we calculate as we go through in reverse order. So just to highlight that, these two arrows are shared between both of these gradient calculations. And these two arrows represent the exact same thing that we've computed here. And so the idea of backpropagation is let's reuse those computations as we move backward through the computational graph. So first we're going to calculate the derivative of the loss with respect to the weights of the final layer. We're going to store the derivative of the loss with respect to the sum at that layer. And then we're going to go through each of the layers before in this backward order and calculate the gradient with respect to the sum, or with respect to the weights. And then we're going to store that term, the derivative of the loss with respect to the sum. And then at the very end, we're going to return now all of the derivatives with respect to each of the weights. And then if you're using stochastic gradient descent or any type of gradient descent algorithm, you would just apply those gradients with some learning rate to your weights to update them and improve your loss. So again, we're updating the weights using the gradient of the loss here. This backpropagation is used to calculate these gradients, which you might hear sometimes called as credit assignment. And this is all done just using the basics of chain rule. So the gradient is propagated backward. And most deep learning libraries that you'll use will actually take care of this all for you, so you don't ever need to actually calculate what is the gradient of my loss with respect to my weights. And this is called automatic differentiation, or autodiff, but it's very important to know what's actually going on under the hood so that you can kind of diagnose if something is going wrong in your network. You're not just dealing with a black box that's automatically differentiating everything. So I would encourage you to look at backpropagation. Just familiarize yourself with it at least a little bit. Okay. Let's think about the implementation of what we might have here. So there are numbers of ways to parallelize the operations that are going on here. Again, this is all matrix multiplications and pointwise operations that we had. So if you just recall this picture of what an artificial neuron is, we have this ability to parallelize across the units. So we talked about having a weight matrix instead of just a weight vector. So now we're calculating for all the neurons in a particular layer. We're calculating all of their sums together. And so that can be parallelized in modern computing architectures. And likewise, we can think about data parallelization. So we'll actually feed an entire batch of data instead of one particular data example. And so here we see that we have now a matrix of inputs. And in the most general case, you'd have a matrix of weights and the matrix of inputs, in which you're calculating now a matrix of summations. And yeah. So just to think about what this actually looks like in code, if you were using NumPy to implement this, this is what a basic neural network layer looks like, where you have now this input that's coming in, you have this set of weights, you're just dot producting the weights against those inputs, and then in this case we're taking this nonlinearity, which is just the maximum of the input and 0. So we're just taking the positive part of this. But actually you might want to instead encapsulate this in a class where the weights are maintained by this object itself. So here we'll have actually a class, which is our neural network layer, and that's going to consist of these internal parameters w, which we're going to initialize in some way. And then now the call function to this is going to give us, again, this dot product and then the nonlinearity. But actually, for this implementation, we would need to calculate all of the gradients ourselves. And so that's quite tedious and can be error-prone. So in general, most deep learning libraries, as I said, will automatically handle the differentiation for you. Most of them have a lot of machinery set up for this ability to construct these networks very easily. So there's a ton of software libraries out there. They're more or less all implement the same low-level functionalities. So there's a lot of options out there. And in all of these settings, you're just building this computational graph, defining the loss, and then everything else gets taken care of for you in terms of calculating gradients. All right, question?
Can you give us the brief difference between the packages?
Yeah, so they each have their benefits and drawbacks. I would say there's been a number of kind of paradigm shifts in how people have thought about structuring the software. The move, especially with a software library called Theano that was introduced almost 10 years ago now, was to think about this in terms of these kind of basic mathematical operations. You build up this computational graph out of these basic operations like matrix multiplications, exponentials, logarithms, other nonlinear functions, and now once you define this graph, you take care of the automatic differentiation for you. So TensorFlow really builds off of that kind of paradigm where they construct this graph. But PyTorch and a previous software library called Chainer developed this notion of having a dynamic graph. So instead of building the graph once and then running all of your data through that, in PyTorch and these other dynamic graph libraries, you're building up the graph as you make these computations. You're holding on to these weights in memory, but you're building up the graph anew each time, which is helpful if, for instance, you're calculating a different length of of like a sequence per data example. And TensorFlow tried to implement some of this in what they call eager mode, but it's still kind of more based around this computational graph that's static kind of paradigm. And then these other libraries are, they make different trade-offs in terms of ease of use and kind of how much access you have to low-level functionality. So things like Keras are built on top of these low-level libraries, where with like TensorFlow and PyTorch, you have access to kind of the low-level computational primitives. In Keras, you just have layers, so you can't exactly manipulate things at as fine a level of detail. Yeah. Any other questions on software or anything like that? Okay. So I wanted to get into some of the tips and tricks. So we talked about the basic mathematics behind this, but we didn't really get into like what actually works in practice or what do people actually do. So there's a lot of design choices that need to be figured out. So the first thing I'll get into is this aspect of the nonlinearities. These are absolutely essential in constructing these networks, because without them, the entire network would just collapse. And so to see this, you can think about this picture of what we had of this output that's being calculated through a series of nonlinear operations and these matrix multiplies. And now if we remove those nonlinearities, we just have a series of matrix multiplications. But you could imagine doing all of those matrix multiplications beforehand, and then you just have one matrix at the end that you multiply against your set of inputs. And that's obviously a linear function. It's actually not exactly linear, because there's some precision rounding that happens, but for the most part, you can consider this a linear function. And so we really need to think about what are these nonlinearities inducing in terms of what functions are we calculating as a function of these distances in our network. And these might be inducing different optimization surfaces as well. So we need to take that into consideration. So the old school kind of nonlinearities were things like this logistic sigmoid, which we saw in the example of logistic regression, and the hyperbolic tangent, which looks very similar, but is between -1 and 1. And the more new school nonlinearities are these things like the rectified linear unit, or ReLU. You have additional nonlinearities where you now, instead of having 0 along the negative portion, you have some small negative slope, or some small positive slope. And you have other things like soft plus, the exponential linear unit, or LU. And the basic distinguishing factor is that these old school nonlinearities are what people typically call saturating, where at positive infinity and minus infinity in the input space, the derivative goes to 0, so it's flat. So it's totally saturated at that point. Whereas these newer nonlinearities that people started using more recently are non-saturating. So either at positive infinity or negative infinity, or both, they have non-zero derivatives. So you might be asking, why did people start using these non-saturating nonlinearities? Well, that gets to this question of what's called vanishing gradients. So with these saturating nonlinearities, like this logistic sigmoid, again, we talked about how you have small derivatives as you go out from the origin toward positive infinity and minus infinity. And so you're going to have small derivatives almost everywhere in your nonlinear function. Now, you can think about if you were to chain multiple operations together to form a very deep network. If you have the product of many small terms, each of which is between 0 and 1, and most of them are towards 0, eventually this product is going to become increasingly small. So you have now, I've kind of just shown just the terms where it's derivative of the output with respect to the sum. So this is the derivative of the nonlinearity. If you have the product of many of these terms, your gradients are going to essentially vanish as you go further and further back in the network, which is going to make it harder to train this nonlinear function. So people really struggled with dealing with this, but nobody really had the best intuition as to why you couldn't train a very deep network. I mean, they should be better at fitting data. They should be more and more nonlinear. Why should it be the case that you have such a hard time training this? It's due to these vanishing gradients. So the kind of first nonlinearity that people started experimenting with to try to get around this was this rectified linear unit, or ReLU again. So this is just the max of your input and 0. And so above greater than 0, you have a derivative of 1. Below 0, derivative of 0. And so now we don't have vanishing gradients in this positive region. But in the negative region, we actually have a gradient or a derivative that's exactly equal to 0, which you might think maybe that's going to cause a lot of problems. It can, but in practice, it actually doesn't seem to be a very significant problem, and you can train fairly deep networks with rectified nonlinear or rectified linear units. So the next idea that we'll get into is this one of normalization. So we saw how, if the inputs to this nonlinearity get to be too far away from the origin, we're going to saturate our nonlinearities. What if we just kept them in the range where the derivatives are large enough? So we're going to keep it in the dynamic range of the nonlinearity in this gray region that I've highlighted here. Could we just do that? So we could think about actually normalizing the activations before we apply the nonlinearity, which would shrink the set of points that we have toward the origin and keep them, the inputs to this nonlinearity, in this dynamic range. That's one option we could do, where we apply some shift just to 0 center the data and then scale it in some way depending on how far or how spread apart our data points tend to be. So that's the idea behind what's called batch normalization, and also many other forms of normalization as well. So in this case, we're going to normalize each layer's activations according to the statistics of the batch of data that we've input to the network. So we have this sum S at layer L. We're going to take the mean and the standard deviation of the batch of data that we have. So we'll normalize across the data dimension. And then we're going to, again, so we'll apply this normalization, this scaling and shifting, or shift and scale, and then we'll apply this affine transformation just to allow the network to essentially undo the normalization that just took place. So we're going to keep now, hopefully, the internal activations in a similar range, and that will speed up training. And we're also, by normalizing according to the batch, which is randomly selected, there's a small amount of stochasticity, or just randomness, that's injected into the training process, which hopefully will improve generalization. You don't want to get too used to whatever batch you're with, because it's always going to be random. So why does this actually work? We talked about keeping activations in the same range, but does this doing what we thought it was actually doing? The original motivation for this was what's called internal covariate shift. So this idea of covariate shift just means that you have some distribution of data, and if that's shifting over the place, you're going to have to be adapting your weights to the shifting of the data, as well as just learning what the distribution itself is. And internal covariate shift just means you have that taking place within the network as well. So while you're training, the activations at the first layer are going to be changing as a function of how you're changing your weights at that layer. And now you can think about, okay, your outputs of your first layer are going to be changing, making it harder to learn the weights at the second layer. So that could be an issue. So you can visualize this as like this is the distribution, a histogram of activations at the beginning of training for some particular layer. And during training, this thing's going to get spread apart depending on what these data points actually are. And maybe by the end of training, it's going to be shifted a bit. So we'd like to be able to perhaps keep these activations within the same range. So hopefully batch normalization would allow us to do that. And this was the accepted wisdom until about a year ago, I would say. But actually, batch norm doesn't actually seem to be doing this. So there was a recent paper that showed that this isn't actually the case. It's not really statistically different from the internal covariate shift is not different from not using batch norm. So this paper they looked at actually, could you quantify the internal covariate shift and then compare it? But what they did find, it may not be reducing internal covariate shift as the original authors of the paper from however many years ago said, but it actually does seem to be stabilizing the optimization surface. So it's smoothing out this optimization surface, making it easier to learn, and also biasing the network towards certain types of solutions you can think of in weight space. So if you actually visualize what the loss looks like, which is kind of a proxy for this optimization surface, it's much more jagged without batch normalization. So this might point to kind of some intuition as to why batch normalization tends to improve training speed and also generalization. So this kind of is one example of showing how the nonlinearity actually really shapes what your loss surface looks like drastically and can have a profound effect. OK, so let's talk about regularization. So batch normalization offers some form of regularization by biasing your model toward finding certain solutions. But we know that deep networks are incredibly flexible. So we might have to incorporate other forms of regularization to prevent them from overfitting to the training set when we'd like them to generalize to the test set as well. So regularization is just, just to review, some method of combating overfitting. And what you're doing is you're formalizing prior beliefs on either your model or the type of data that you're dealing with. So one form of this is you can generally classify as adding stochasticity to the training procedure. So some amount of uncertainty, whether it's batch normalization or just the optimization procedure you're using. If it's stochastic gradient descent, then you're not exactly following the gradient all the time, which has been shown to bias you toward certain types of solutions. And another form of this stochasticity is what's called dropout, where at each or at some layers you might just totally drop the activation. So you just, instead of actually passing on the calculated unit, you would just send a 0. And in this case, you prevent what the authors call fragile coadaptation, where neurons learn to depend on the other neurons within their layer. In this case, you're preventing them from depending on each other and overfitting to the peculiarities of your training set. They're hopefully learning more generalizable features that are not just found in the training set. So other types of regularization, you can think of constraints like early stopping, where you have some validation set that's preventing your model from converging all the way to the solution that it might find just on the training set. Or other things like weight penalties, where you keep the weights within this ball of, if you have like the L2 norm of your weights. That's another form of regularization, which I think you may have gotten into in other lectures. Another thing to be cognizant of is that you need to be aware of how you initialize your weights. This is like the biggest untold secret of neural networks, is that weight initialization matters a ton. Because if you don't initialize your weights correctly, you might end up having the network blow up in terms of not finding a good solution, or just not even learn at all. So some strategies are by using a uniform distribution to initialize the weights, or potentially a Gaussian distribution. So the main optimization procedure people use to optimize these networks is stochastic gradient descent, or SGD, which you just apply a stochastic estimate of the gradient from a batch of data, and you're descending the loss surface. Some more recent variants of this optimization procedure use additional terms to maintain a sort of memory of what the previous gradients actually were, so that you can kind of speed up this optimization. So you can visualize this. There's a nice graphic here from this website where they show from above, this is what these optimization algorithms are doing in this on this 2D surface. And then you can also visualize on this saddle what these different optimizers are doing in terms of how they're taking in the gradient, using previous estimates of the gradient to result in the actual step that's taken in weight space. Yeah. So I think one of the final things we want to talk about in terms of tips is that up until this point, we've talked about these long sequential structures where we have this just sequential connectivity, and information from the input to the output must flow through every single chain of computations here. So we might actually see cases where information cannot propagate all the way to the end of the network reliably, and in which case we'd like to have some shorter pathways from the input or from internal units to later on units. So have these shorter pathways, information can flow more easily. So one of the papers that really highlighted this was this paper on residual connections from 2016, I believe 2015 even. And in that case, you're taking your previous input here, you calculate some neuron here, this nonlinear function, but then the output is actually added to the previous unit. So what you're doing is you're calculating the residual in this layer instead of the entire function. So you're building up this function with just these residual computations. So you have the short pathway you could take, or you have the long pathway you could take, essentially. And kind of building off of this idea was this more direct kind of approach of just, let's literally just attach connections from earlier units to later units. And these are sometimes called dense or concatenated connections. And in practice, both of these techniques tend to improve the performance of these networks phenomenally, and you end up having networks that are easier to train. OK, yeah?
Does that result in a dramatic increase in computational time?
So not typically, no. So this residual connection here, you don't have, if you maintain the same size throughout, then you don't have any additional weights that you need, and it's just a simple addition here. So it ends up not being substantially more computationally intensive. Once you start getting into these connections here, it can be a bit more, you need to think about maybe paring down each individual layer and kind of reshaping the architecture in that way.
So
Yeah.
what's the downside of it?
What's the downside of this? I wouldn't say there's necessarily a downside. Maybe it just takes a bit more thought in terms of how you construct the architecture. But in general, residual connections or these dense connections will essentially always help. And one way people like to think about it is almost like a Taylor series expansion, where you have kind of these dominant lower order terms that you're calculating, and then you have these higher order residual terms that improve your solution a little bit, but are not absolutely essential. So instead of just calculating a high order function, you calculate more of like a Taylor series expansion of a function. Yeah. Any other questions? Yeah. Okay.
For initializing the weights, what is the wisdom on the size of the variance of those?
Yeah, so there's a couple papers from like 2013 or so, but the main idea is just that based on the number of output units, number of input units, you need to scale the variance according to that. So just that you maintain a similar range of activations when you actually do the summation. So it basically just comes down to this calculation. There's a few papers that go through what are like good strategies for doing that. One of the main strategies is called Gloro. Initialization, which is just named after a guy. And then there's another weight initialization scheme called Kai-Ming, which is just for a different set of assumptions. But yeah. Other questions? Another question? OK.
Yeah. So if you have this residual highway, and then you're not going to have as much of a problem with vanishing gradients, are you? Because
That's absolutely right. Yeah. So in the original residual net paper, that's exactly what they explored, which is that with these rectified linear units, you're supposed to be able to train very deep networks, and we know that deeper networks tend to, they have more expressive capacity, but when you start adding on more and more layers, you're just making this problem more and more difficult to learn. So exactly, they found that by having these residual connections, you could actually have much, much deeper networks than what anybody had trained before. I'll get into this on Thursday, but there's kind of a sequence of depths that people started to be able to train. So it used to be that a deep network was anything like 2 or 3 layers. You were pushing your luck if you even got to 4. But then, once people started to actually develop these techniques a bit better, they got into the range of like 10 layers, and then eventually 20 layers, and then 100 some layers, and now you can train up to like 1,000 or more layers, and still actually have gradients get all the way back to the input. Yeah. So I just want to get into what I'll call a buffet of different ideas. So there's been just an explosion of research recently in deep learning, and people have taken these networks and ran in like a million different directions. So there's obviously much, much more than I can get into here, but I just want to show like some of the cool things that people have done. So one thing is this idea of attention. So we've seen like kind of a basic set of mathematical operations up until this point, but what people started to look at more recently is this idea of actually having this weighting attention here, A, that you dot product against some internal vector or even the input of your network. And so now you're going to reweight that according to this attention vector. And in practice, this allows you to solve much more complicated tasks in certain domains. And then there's also even the idea of having a hard attention, where you have perhaps one network that outputs just a set of indices that you want to index from. And so here you're actually, instead of essentially looking at the entire input, you look at just a hard subset of the input. And this is also helpful. Like if you can think about your retina has to, your eyes moving around, sampling the scene, and that's a discrete problem. Like your eye, when it's looking over there, can't see what's over here, so you need to have some mechanism of thinking about how you want to actually choose what to attend to. And then another thing that's become increasingly important is differentiating through non-differentiable operations. So there's stochasticity that arises all the time. There's other issues. And so you see, like, if you have a distribution that's perhaps somewhere internal to your network and you want to be able to calculate gradients through the sampling of a distribution, well, we don't actually know how to do that because sampling is this non-differentiable operation. Likewise, if there's just a discontinuity somewhere in the network, like you have just a hard threshold at some point, how would you backpropagate through that? Because you have 0 gradient most of the places and then an infinite gradient at one place. And then also things like reinforcement learning, where what I'd like to optimize is my reward that I'm receiving, and that's a function of the environment I'm in and what action I took. But I actually cannot backpropagate through physics. Like I can't backpropagate through the environment here. It's a black box for all I'm concerned. So I need some way of estimating what is the gradient of the reward that I received with respect to the action that I took. And that's also this non-differentiable operation because we don't have access to the true environment. So how have people tackled this? The main kind of computational graph that you can think of is this, where you have some parameter theta here, which goes into this stochastic node z, and that gives you out some function f of z. And we'd like to be able to calculate, under the distribution of the node z, what is the gradient with respect to theta of our output f of z. So the score function estimator, or what's sometimes called the reinforce gradient, says, it uses some mathematical tricks in terms of taking the log and the derivative and re-expresses this gradient, which we can't take exactly because it goes through this stochastic node, into this other gradient, where now you take this product of f of z and the gradient of the log probability of z. And this is an unbiased estimate of what the gradient is. There's going to be there's typically some amount of variance associated with this estimator. And so this is what's often used, for instance, in reinforcement learning with the policy gradient, if you've ever heard of that, which is a method of training a model-free method to optimize reward. So in that case, you have, for instance, this f of z is like the return that you got from a sequence of actions, and this probability is what is the action that you took. Another method for doing this is what's called the reparameterization trick, or the pathwise derivative estimator. And in this case, you're actually reparameterizing the stochastic node z as a deterministic node that depends on some other stochastic node epsilon here. And so you can now express the expectation over epsilon and then bring the gradient in and actually calculate that. And so an example might be if you're trying to estimate the gradient for sampling from a Gaussian, you could rewrite the sample as the mean plus epsilon times your standard deviation. And this will give you an equivalent formulation of a sample from a Gaussian. It still has this stochastic element to it, but now you can actually backpropagate through this deterministic pathway here. Another cool idea out there is this idea of learning to optimize. So if we treat optimization itself as a task, we can think about having the change in a parameter be a function of the parameter and the gradient. And now we have this function here, which typically in like stochastic gradient descent is just like a linear function of our current estimate and our gradient. But we might be able to actually learn a better function. So if we treat f as this optimizer function and theta as the parameters of this optimize function, then we can learn to actually perform optimization, where you have a one neural network here that's being optimized, this optimize, and another neural network out here that's the optimizer. And in practice, these, when you can get them to work, they work better than traditional optimization algorithms, because now you can apply these nonlinear updates depending on what your gradient is. So this is a really cool idea, and kind of it's spawned off a few different works recently. Another kind of strange idea is this one of adversarial examples, which maybe you've heard about in the popular press. But the basic idea is that you have this network. Here I've drawn it as a series of boxes, but you have this output here. And you're actually going to take the gradient of the output with respect to the data itself. So the input that you fed into the network, you want to try to change the output of the network by changing the data itself. And so what you'll see is that you can have a classification algorithm, a classification model that's trained to classify the object, or the animal in this instance, of a panda. And by adding just a tiny, tiny bit of white noise, or seemingly white noise, but specifically designed for this network, you can switch the output classification for this particular example. It doesn't look any different qualitatively, but you can essentially fool the network into thinking this is a gibbon with 99.3% confidence, which is a bit frightening if you think about, these models are supposed to work really well, hopefully be very robust, and yet they're breaking on these adversarial examples. And you can actually extend this even into the real world, where if you take a model that's trained to classify stop signs and you place stickers on the stop sign in very well thought out ways, you can you can fool this stop sign classification model into thinking this is a different sign or nothing entirely, which is a bit frightening if you think about this being deployed in autonomous driving setting. So there's been a lot of work in thinking about, okay, why is it that we can find adversarial examples? There's some theories out there as to why. And then how can we prevent these types of things from actually being an issue with our models? And so you can think about this, like, there's actual real use cases where if you have like an online content moderator that needs to moderate whether or not an image is appropriate or work safe, if you can fool that automated content moderator, then you can post whatever you want, and that's maybe not the best idea. Another idea that we'll get into briefly is this idea of Bayesian neural networks. So up until this point, we just talked about having like a point estimate or an individual number for each of the weights. Well, we could actually associate each of those weights with an entire distribution, and in that way maybe have a more a stochastic kind of operation of our network, and maybe be able to quantify the uncertainty instead of just having a point estimate that tells us nothing about how certain or uncertain the network is in its estimate. So we have these prior probabilities on various quantities, and this can hopefully prevent overfitting in the low density data regions. So if you've never seen an example before, you don't want to output something you don't want to output just a point estimate. You want to say, okay, here's my estimate, but there's a high variance to what that estimate actually is because my weights have some uncertainty associated with them. Okay, and one other idea is this thought of generalization. So we've talked about how flexible neural networks are, and the conventional wisdom was that you learn this hierarchy of features, and you're building up layers of abstraction. It's actually learning what to look for by carving up this space. But there's actually the capability for these networks to learn from pure random noise. They can classify pure random noise with 100% accuracy, given enough parameters, obviously. But the training behavior actually looks slightly different. So here I'm showing the average loss for just an image classification pipeline, and this blue curve is where you're training with the true labels. And you can see other curves here are if you have completely random labels, if you shuffle the pixels around. In this example, it shouldn't do as well, and yet it can still train to 100% accuracy. If you're adding noise to the inputs themselves, and you see that these networks have the ability, if they want, to fit essentially anything. But depending on what your data is, what your labels are, they'll have different behaviors. And briefly, I'll just get into this idea of the information bottleneck theory. So there's not too many real theories of deep learning. One of the theories out there is this one of the information bottleneck, where what your network is trying to do is maximize the mutual information between the input and the output while discarding all other information. So you can think of these deep networks as trying to preserve this relevant information. And in a number of papers, people have tried to point out that, well, if you look at the mutual information during training, these networks where each color here is a layer, these networks start off with for instance, the first layer has a lot of information about the data and also a lot of information about the label. So all of the information about the label is hopefully contained in the data unless the label is somehow not related to the data. And you see that as you go initially in training, less and less information relevant to the label is contained in the later layers as well as to the data. And as you train, you start increasing the amount of information about the data that's in these layers. But then there's this second phase here where you start pushing off here and discarding the information about the data in order to get just the information about the label, until eventually you have, along the top here, a sequence of layers that go from capturing everything about the data in the label to just everything about the label. Yeah?
How do you end up calculating your mutual information if you have these features that have different dimensionalities?
Yeah, there's a lot of kind of hacks and tricks to it, and not everything is actually well defined. So I'm not exactly sure what approximations they use in these settings, because if you're using continuous variables, it's a bit tough to actually do that. So I'm not 100% sure. Okay, and so I got a little bit of time. I wanted to get into more of like a perspective look on this, because deep learning is incredibly popular right now. I kind of want to just dispel some myths and get back to the big picture, and then I'll finish. So just to go briefly over the history, because I think it's important to see how these ideas have progressed. A lot of the field of artificial intelligence and even like modeling neural networks started with Alan Turing. And he had this kind of notion of let's actually try to approach this as a learning problem, and we'll start from like a very simple model and then eventually build it up through this education or machine learning to something that's more complex. So already in the 40s, This was like around the time when computers were just starting to be developed. People were starting to think about, could we actually model biological neurons as simple mathematical functions? So back in 43, there was like this influential work by McCulloch and Pitts where they talked about this threshold logic unit. And they're trying to mimic biological neurons where you have some set of weights here that are coming from different inputs, and you're calculating basic Boolean functions out of this. Frank Rosenblatt took this idea and took it further with having these weights that could actually be trained, and then having this nonlinear function again that would give the output. And then by the 50s, people were getting really excited about neural networks. These things are going to solve everything. We're going to have intelligent machines within a decade. But then in 69, Minsky and Papert showed that you actually cannot learn the XOR function with this simple one-layer neural network, which is what I showed you at the beginning of class. And people got very kind of depressed, and were like, OK, neural networks just aren't going to work. Let's move on to other things like symbolic logic and things like that. So this is what people typically call the first AI winter. But then moving like even a decade later, people like John Hopfield here at Caltech started thinking about, let's go back to some of these neural network models and see what they can do. So he introduced this idea of the Hopfield network, which is this form of associative memory. So it's actually a recurrent network, and we'll get into recurrent networks on Thursday. There was the restricted Boltzmann machine, which is a generative model, which we'll get into, I think, in March sometime. But that was a big milestone. And then backpropagation in its kind of current form. It had been developed a few times previously, but it really actually was highlighted in 1986 here with these three. And then eventually later in that decade, Jan LeCun developed convolutional neural networks. In the 90s, people started looking more and more at recurrent neural networks, like this long short-term memory, or LSTM, which is still very much in use to this day. And then people started developing more complex generative models, like the Helmholtz machine, which has some connections to neuroscience as well. And then after that, there was kind of a lull in interest in deep networks. People started getting more into SVMs and kernel methods, largely because it was just really difficult to train these models. There wasn't a whole lot of data. The computers were not that fast back then, so people started to look at other methods. But then, more in like the middle of the aughts, the Hinton and some colleagues developed this method for training neural networks in a layer-wise fashion. And then later in that decade, more and more people started to move toward GPU computing. Bigger data sets started to be made. People started to experiment with other nonlinearities. And then in like 2011, 2012, there started to be some drastic success on speech modeling and on image classification. And since then, there's just been a flurry of research in everything from generative models to reinforcement learning, and even just looking at how can we improve these architectures much more. And so it's really a golden age, or a golden era for the research in neural networks, which for the most part continues to be the case today. And so just to get big picture to wrap up here, we looked at deep networks, which if anything you should take away from this lecture, they're just function approximators. You're trying to learn a nonlinear function in most cases. And often that function is actually a conditional probability distribution. So we're dealing often in machine learning with these probability distributions. Deep networks are flexible ways of learning those probability distributions. A lot of the success and a lot of what we saw in this lecture was supervised learning, where you have some input, you pass it through your model, that gives you a distribution over the output, and then you have some empirical distribution of a label that you might have of some high-level latent variable, and you want to try to fit that distribution exactly. And so you're going to take usually the cross entropy between these two distributions, and that's going to be your training signal that goes back into your network to allow you to update your weights. But this is just supervised learning. The idea of deep learning is actually can be applied to any kind of learning paradigm regardless of supervised, unsupervised, reinforcement, what have you. So in deep reinforcement learning, here model-free deep reinforcement learning, you can use these deep networks to estimate value functions. So what is the long-term value of taking a particular action in a particular state, or just to parameterize your distribution over actions directly as a policy. And really, you should just think of deep networks as a tool, a really useful tool that people have been working on and developing and improving over the last few years. But the real progress in this area depends much more on the learning algorithms themselves. Once you develop the algorithm, you can just swap in whatever network architecture you need for the case. So why are people excited about deep learning? Well, it's allowed us to extend a lot of learning algorithms that we already had to new and relevant domains, like image classification and detection, speech modeling and classification, text modeling, and even robotics. So some people have applied this to like grabbing, picking up objects. And really, deep networks are just allowing us to learn more complex conditional probabilities. The algorithms themselves are largely the same as they were before deep learning. Not a whole lot has changed. There are some cases where new learning algorithms have been developed as a result of all this work in deep learning. And the main one I would point to would be generative adversarial networks, which I'll touch on in a later lecture on generative models. But this is kind of a new idea that's come out of having networks that essentially are engaged in an alternating optimization procedure. So we have these amazing tools, but still there's a lot of tasks that are unsolved. And the algorithms themselves, the kind of theory behind all of what I showed you is just one component of what actually determines future progress. And if you ask anyone in machine learning right now why it is that deep learning took off, they'll probably point to the data sets, the hardware, maybe the software and compute before the theory. The theory kind of came after the fact. Once you can actually run these experiments, then you can test out different nonlinearities really easily, test out different architectures. And so it's important to keep in mind that these other factors have just as much, or if not a larger importance in determining future progress. So deep learning as it is right now, it may get replaced, but the basic idea of trying to estimate a conditional probability is still going to remain. So whatever replaces it will be something that allows us to estimate either more easily or more complex these conditional probabilities. And on Thursday, I'm going to be talking about some specific network kind of structures, particularly convolutional networks and recurrent neural networks.